Hello and welcome to another video. In this video we're going to be working on min cost climbing stairs, and we're going to be going through all the solutions for this just because it's an easy problem. So if you're new to DP, this is going to be a good video for you. Usually I don't really explain the super basics, but in this one I will because it's an easy problem. So you're given an integer array cost where cost I is the cost of the I step on a staircase. Once you pay the cost, you can either climb 1 or 2 stairs. You can start from step 0 or step 1, return the minimum cost to reach the top. So in the first example, we have 10, 15, 20. So you can either start at 10 or 15. Essentially, the top is the node right after the last one. So here, if you start at this step, you would obviously, the optimal solution would be to pay 15 and take 2 steps and come here. And so that would be 15. And if you start here, you can pay 10, and then you can either go here or here, but then you'd have to pay another 15 or 20. So the optimal solution is just start at step 2, take 2 steps, get to the top. Okay, now let's go through the other one. So we have 1, 100, 1, 1, 1, 100, 1, 1, 100, and 1. And so ideally, you probably want to skip all the hundreds, right? So it says you want to start at index 0. So let's see what it would look like here. So essentially, you would want to start here. You'd want to skip the 100, right? So you would want to pay 1 or pay 2, go over here. So you paid 1 total so far. Then you want to probably pay another 1 and come over here. So pay another 1. Then pay 2 and come over here. Or 1 and come over here. Then you want to pay 1 more and come over here. And then probably pay 2 and come over here, or 1, but just jump 2 stairs, and then finally pay 1 and come over here to this end. So you would pay 6 total, right? So how do we do this problem, right? Like, obviously we can try to like do all this. Well, first of all, let's figure out like at every step what are our choices essentially. So let's say we have this like first one, so 10, 15, 20. At every step, we essentially, our answer is, the solution for starting at a step, let's say, right? Like, let's say we start at this step. What's the solution for min cost to get to the top? Or this one, I guess. Let's start with this one. What's the solution? Well, it would be a recursive function, but essentially it's going to look like something like you pay the cost, right? So you're going to want to pay the cost. So pay whatever that value is that we're at, plus the minimum of taking 1 step and taking 2 steps. And how is that going to look like recursively? Well, that's pretty simple, right? So if we have these indices, if this is like index 0, 1, 2, essentially we'd say like, okay, well, the value of getting to the top from here is 10 plus the minimum of, and whatever this function is, let's call it f, right, on 1 step. So this would be index 1, or so this would be 1 step, or taking 2 steps. So it's going to be f starting at index 2. So essentially, you just pay the cost and you take the minimum of calling the recursive function on the next index. And you keep doing that, and you keep doing that, and you keep doing that. So let's kind of look, we're going to do a decision tree for this even small thing, and we'll see what issues we run into, right? So let's just say we start at index 0, and we're going to draw branches, and we're going to write the cost, and we're going to like figure out where we're at next, right? So we're starting at index 0. And we need to get to index 3, essentially, right? That's the top. So at index 0, we can either take 1 step, so we have to pay 10 either way and get to index 1, or we have to pay 10 regardless and get to index 2. Now, at index 1, you can either pay 15 and get to index 2, right? You take 1 step, or you pay 15 and you get to index 3, which is the end. Then at index 2, you can either pay 20 and get to index 3, or you could pay 20 and get to like out of bounds, right? 4. Let's call that 4. If you take 2 steps here, you're too far. So if you come too far, that's an invalid solution. And the same thing, let's look at index 2 here. We would pay same thing, right? 20, 20, get to index 3, and get to index 4. And you could see that like even for this very small thing, you could see index 2 shows up twice. And this tree and this tree is exactly the same. So once you get to index 2, it doesn't really matter how you got there. The cost from getting index 2 to the end is the same, right? So you're doing repeated work here. You're doing this work here, and you're doing this work here. So wouldn't it be nice if, like, the first time you got to index 2, you would calculate it, and then the next time you get to index 2, you could say, like, oh, I already calculated that. Let me just get that value and reuse it. Similarly, do we have any other repeated work? Well, let's take a look. So we have index 2 repeated. I think that's it in this one, because these are all at the end. But essentially, as your array gets even bigger, like if I did this second example, we're going to have a lot of repeated work, right? Like, for example, you can get to this index this way, or you can go 1 and 1. And once you get to further indices, you can get there in a lot of ways. Like, let's look at like this index, see how many like ways. We're not going to look at all of them, but there's just going to be a bunch, right? Like, you can go 2 steps and 2 steps, or you can go 1 1 1 1, or you can go like 1 1 2, or 2 1 1, right? So once you get to later indices, you can get there like a billion different ways, and you don't want to be recalculating every time. So essentially, to solve this problem, to solve this recursive problem, we're going to have a cache. And what we're going to do is every time we get a solution for some index, right, we will cache it. That way, if we get asked the same problem, we have it saved, right? So essentially, it would be something like, you know, let's say you have some function and you give index 10 and it's not in our cache. We're going to calculate it, we're going to get some output, and then we're going to store index 10 and the result. And then if it gets called again, we're going to be like, oh, that's in our cache, we can just return it. And so now you don't have to do this recursion because, so in this case, it wasn't super expensive, like 2, you don't have to go super far. But imagine the case of like this, let's say this, you have this big array of like 1,000,000 elements, and you get to this number by jumping 2 steps, or you get to this number by jumping 1 and 1, and you're doing all of this repeated work twice. And then you're gonna have to do like more repeated work in here, more repeated work in here, right? So this is gonna save us a ton, essentially. This is gonna make it so we have a linear time solution, because assuming we can have I different indices, we're only going to have to actually calculate the value one time, and then once we calculated it, then we can just cache everything. So that's going to save us a lot. So in all these dynamic programming problems, whenever you draw your tree of decisions, if you get to the same place multiple times, and it doesn't matter how you got there, this is the key. The problem has to be in a way where it doesn't matter how you get to some index, the cost of getting from that index to the end is the same. And in our case, it is. Because there will be some problems where you're like trying to find a word, and then it's not the case. But in our case, it's the same. So essentially, what it's going to look like is we're going to have a recursive function with caching, and at every single index, the way to figure out the value for that index is just whatever the cost you have to pay now, plus the minimum of going up 1 and going up 2, so we can just recursively call that function going up 1 and going up 2. Now you also want to have base cases for our function. We're going to have 2. So base cases for our function, we can write it over here. 1, we get to result, which in our case is actually, so if this array is 3 elements, you want to get to index 3, that's the top. So index 3, the one right past it, is the top, right? Because they say pay 15 and climb 2 steps to reach the top, so you're going to be right over here. So that is fine, and in which case, what would we want to return, right? If we are at the result, we want to return 0, because the cost of getting from the top to the top is 0, right? We don't have to pay anything. 2, we jump over the result. And you can handle this in your actual recursive call, but we're just going to handle it in our base cases. So if we jump over the result, like let's say we are at 20 and we take 2 steps. Well, we skipped the result, so we went too far. So that shouldn't work. So because we want to return the minimum, we can handle this by just returning infinity. That way, this is always going to be like the worst thing to do. So then some other thing is always going to beat it. So that's how you can handle base cases that are like invalid. If you're trying to minimize, you just return infinity, and if you're trying to maximize, you return negative infinity, to ensure that your recursive function will just ignore this essentially by, it's never going to like take the minimum of infinity and something else, right? It's always going to pick the other thing. So these are our base cases, and our recursive cases just take the minimum. And so that's how you do the DP for this simple thing. So let's actually go and code it up now. And here we have it. So we're going to have a visited cache. We can even call it cache. And we're going to have a DP function. It's just going to take an index. And we're going to put in the base cases first. So we're going to say if I equals length cost. That means we are right at where we want to be, so we return 0. If I is greater than length cost, then we jumped too far, so we're going to return infinity. And the other base case I forgot to mention is if we have that value cached, right? Like if we already calculated before, we're just going to return that. So we can just say if I in cache, let's return cache I. Okay. Now we are just going to check our two cases. So we can just say visited or not visited. We're going to say cache I equals. So remember, if you're at a stair, you have to pay the cost. So it's going to be cost of I. And then it's going to be the minimum of taking one stair. One stair would be the index goes up by 1, or 2 stairs, which would mean the index goes up by 2. So dp I plus 2. We're just going to take the minimum and then return it. Right? And now all we have to do is we have to remember we have to return the minimum of starting at stair 0 or stair 1. So we can just call this function twice. And this will actually be really fast because calling this function twice, essentially what would happen is once we call it on 0, it's gonna calculate the cost of starting at 1 like right away, right? Because if you call on index 0, it's gonna do the minimum of dp1 and dp2, right? So once we call it on 1, it'll already be cached. So calling it on 1 costs us basically nothing. But essentially now we have to return the minimum of calling this function starting at index 0 or starting at index 1. And now we can try that. And it looks like we have something that works. And you can see this is kind of slow, and this is really memory inefficient. So now we're going to go to the second part of this. So now that we have this like recursive solution, we're going to talk about how we can improve it. And we're going to talk about how we can improve it with this bigger problem. So let's actually copy this. So we're actually going to draw it. Or I guess we can just get rid of all this, right? Or let's just copy it down here. So let's copy it, put it down here. There we go. And let's rewrite this array and kind of explain what we need to be doing if we don't have, if we don't want to do this memoization. Because the memoization with a cache, our cache is going to take up, like if this is length n, we could have every single value cached here. So this will be n space, which isn't ideal, and I'm going to kind of explain why that is. So let's redraw this and let's go to this example. So 1, 100. 1, 1, 1, 100, 1, 1, 100, and 1. And so now, this is our thing. So basically what we are going to do is instead of trying to figure out like how many steps does it take, we're going to start at the very end and build up. And I'm going to show you how that's going to work. So essentially what we're going to do is we're actually going to make an array of the same length as our original array, but instead, let's actually maybe even draw it, let's draw it like this. It's going to make it easier. Yeah. So we're going to have this same array. So we're going to have 1, 100, 1, 1, 1, 100, 1, 1, 100, and 1. And we are going to make one more slot that we are not going to use in this top one. So this top array, this does not exist. So this is like our actual original array. And now this is going to be our DP array. So we're going to make a DP array length of the same as this one, but we're going to add one more element. And I'm going to show you why. So we're going to say 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. We're going to make this 0, and we're going to make this infinity. Because this represents jumping over. Actually, I think what we need to do here is we need to, no, I think we actually need to add 2 states if we wanted to do it like this. So essentially, this is our goal, right? This is the step we want to get to. This is like the step right after the last one. So this is the step we want to get to. So this one is good, but this one is not. And both of these are not in our original array. So this one is going to be infinity, and this one is going to be 0. And these are all going to be 0. So basically, we're going to, like, if you ever get here, you should return infinity because you went too far, right? So that's how that's going to work. And this is going to be, these are our 2 base cases, right? This is the one right after the last one, and this is the one that's too past it where it's way too far. Okay, So now what we are going to do is we're just going to go backwards. So we are going to initialize these to zeros, but I'm just going to draw it like this because I'm going to show you how we're going to calculate them. But we are going to initialize everything to 0 except this one to infinity, and we're going to start at this index here. And now we're going to think like, well, what were we actually doing? Well, and by the way, where's that index here? So that index matches up here. So at every index, remember, we have to pay the value of the index plus the minimum of jumping 1 or 2 stairs. And we have these calculated, right? These are our base cases. So essentially here, we're going to pay the cost, which is up here, and the minimum of the next 2 values, right? This is the value of jumping 1 stair. It's the value of jumping 2 stairs. It's going to be 1 plus 0 or 1 plus infinity. Obviously, we're going to want to take 1 plus 0, so this will be 1. Here, same thing. We have to pay the cost and the minimum of the next 2 values. So the minimum is 0, so we're going to have 100 here. Then same thing, 1 plus minimum of these 2, so it's going to be 2. 1 plus minimum of these 2, going to be 3. 100 plus the minimum of these 2, so it's going to be 102. Here we have 1 plus the minimum of these 2, so it's going to be 4. 1 plus the minimum of these 2, so it's going to be 5. 1 plus the minimum of these 2, 5. 100 plus the minimum of these, 105. And finally, 1 plus the minimum of these 2, which will be 6. So now these are actually our costs. And if you think about it, it makes sense, right? Like this doesn't make sense. Like let's look at the last one. What's the cost of getting from here to the end? It is 1. What's the cost of getting from here to the end? It is 100. What's the cost of getting from here to the end? Well, you would take 1 and then 1 more, 2, and so on. So these are actually these index costs. So this is like at index, this is the cost at index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the last index in the actual array here. And that's the cost of getting all these, and these are our 2 base cases, and these 2 don't exist in our input array, right? This is the actual result that we're trying to get to, and this is the one that's too far. So we did get this, and this is the right answer. Like if you actually scroll up, this is 6. So basically, once we get this, all we have to do is return the minimum of the first 2 values, right? This is starting at index 0, this is starting at index 1. So we just return the minimum, and that's fine. But notice that when we filled these out, like let's say we filled this out, we only use the 2 values ahead of it. So we don't actually need this whole array because in order to get a value, all you need is the 2 values in front of it. So instead of this whole array, we can just use 2 values, and then we can just keep updating those 2 values. And finally, at the end, those 2 values will be the 2 values starting at index 0 and index 1. And the way to notice this space optimization is when you're doing this bottom-up DP or even top-down. Like if we go back and look at our code is only checking the element in front and the one after. So to get every element, you only need 2 elements in front of it, which means you can space optimize this to not use this whole array. You can just use a few elements. So let's walk through how that would work with using 2 elements. So we are still going to use like this part, but we aren't going to use an array. So essentially what we're going to do is we're going to initialize 2 elements that are going to be equal to our 2 base cases, right? So what's going to happen here is, and basically I am gonna like redraw this, but it's not going to be an array. So this is going to be gone. So essentially we're going to have 2 elements, and they're going to be equal to our base cases now. So we're going to have 2 elements. So we'll call this like first and last, and we're going to kind of walk through our array backwards. So let's call this first and last. So first is going to represent our like goal. It'll be 0, and then last will be infinity. Now, essentially first and last is going to be the element in front of last, right? So first is going to represent this case, last is going to represent this case. Now, let's kind of update our stuff, right? So for this element, it's going to be the value of this element, right? So 1 plus the minimum of first and last. So the minimum of first and last is going to be 0. And now, if you think about it, now we only need these 2 elements to get this value. So we get rid of our old last element, right? So we need this value, which is 1. We can get rid of this one, and we can keep track of these 2 now. So how would we do that? Well, we would take this value, let's call this temp or something, right? And we would say, okay, well, let's make first equals temp, and let's make last equal to the old first. right? So we're essentially just shifting the values we're holding. So now first is going to be 1 and last is going to be 0. Then again, for this function, we're going to say, okay, well, temp is going to be 100 plus the minimum of first and last, which is 0, right? First and last, so it's going to be 100 to 0. Then first is going to be temp, and last is going to be the old first. So first is going to be, 100, and last is going to be the old first, which is 1, right? So this is going to be 100. So basically, you just keep filling these out, and you just only keep track of 2 elements. You only keep track of 2 elements, and you don't need the whole array. You just keep updating your 2 elements, and at the very end, your first will be this element, and your last will be this element. Then you just take the minimum one of those 2. And that's how you do like the space-optimized bottom-up dynamic programming. I would encourage you first to do the memoization, then to make an array, then use this first last. So we're actually going to code up this space-optimized one now. So let's actually copy or get rid of this. So we're going to say first and last. So remember, first is going to be our base case where we succeeded, so that's going to be 0, and last is going to be infinity to start off. Now we need to loop, and this is the part we need to make sure that we loop correctly. So for I in range, and so if we look at our picture, what's the element we want to start at? We want to start at this element here. And so this element is at length of array minus 1, right? The very last element in the array. So that's where we're going to be looping. So we're going to say length of cost minus 1. And we're going to be looping all the way to -1, right? Which means we're going to loop through every single element until, so we're going to loop through all of this. And then once we're below 0, we're done. So essentially, once we're below 0, we're done. And remember, in Python, this is exclusive. So what's going to happen is we're going to start here. We're going to go down 1 element at a time. And then once we get to -1, we're done. We're not actually going to use index -1. So we can actually do this in place. So we can just say first last equals. So first needs to be the cost at the current index plus the minimum of the current first and last, right? So minimum of the current first and last. And last needs to be the old first. So we can actually do this in place. And what happens here is this gets calculated and this gets calculated, and then these values go in here. So you can do this without using a temp variable, or you could use a temp variable where you could say temp is this, and then you could say last is first, and then you can update first if that makes more sense to you. But now essentially, once we have our first and our last, that's going to represent the value of starting at stair 0 and stair 1, and we just return the minimum one of those, so we can return minimum of first and last. We can try that. Submit, and that should be fine. So yeah, that one is fine, and this is a lot more optimized. You could see it's a lot faster, it's a lot more space efficient, because now we're essentially only using 2 elements, which is O of 1. So let's talk about the space and time for the memoization and the other one. So memoization, either way, it's going to be O of I, or O of N, and the way to calculate memoization typically is, or just most DP, is what you would do is you would look like, okay, how many states do I have? So my index can be anywhere in cost, which is O of N, and how long do my operations take in my DP? So this is O of 1, this is O of 1, this is O of 1, and this is O of 1, assuming these are cached, right? So these recursive calls, think about, they would only actually run fully once, and then they would be cached. So this would be O of 1 after it's cached. So the only time you have more states than just the combinations of states here is if you have a for loop here, right? If you had a for loop from 1 to n or something, then it would be I times n. But because we don't, these are constant. So this is O of n time for both, right? Because the other one we are iterating through our array backwards, which is still O of n. And space for our memoization, remember we have this cache, and it can store the value at every index, which would be O of n. And for our space optimized bottom up, we only have this first and last variable, so we only have 2 variables. So that's O of 1 space. And yeah, so hopefully this was helpful for you if you are just starting dynamic programming. I think this is one of the best problems to try. So I would make sure to do I would try to make sure to code up all of the solutions, probably do memoization, then bottom up with an array, and then the space optimized, because these problems only get harder. So if you can't do bottom up and you want to learn it, you're not going to be able to deal with harder problems. So this is good ones to practice on. Memoization is the most intuitive, so that one definitely. Usually for the harder problems, I just do the memoization, because usually space optimized bottom up, you can't space optimize the hard problems, and there's not too much benefit, right? You are saving a lot of space, but there's a lot more effort to get the space optimized bottom up compared to memoization. But yeah, it's going to be all for this problem. So if you liked it, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.